All right, so our next speaker, keeping us on the in the spirit of hafnium oxide-based materials, is Pavan Nukala from Groningen, University of Groningen.
Yes. Hello. Hello. It's audible, right? Am I audible? I'll be back. Okay. So today, I'm continuing with the line of hafnia, and I also belong to the hafnia mafia, as we call it nowadays. So I'm going to tell you the story of polar rhombohedral phase that we have discovered a couple of years ago in hafnia zirconia thin films. And perhaps by the end of the talk, I'll try to give you guidelines as to how to stabilize this phase as against the orthorhombic phase that Uwe was talking about. And this is the work which is done in University of Groningen in collaboration with Paris Saclay, Twente, and Luxembourg Institute of Science and Technology. Okay, so a good point to start will be to recognize that there is polymorphism in hafnia and zirconia-based compounds, and these are quite isostructural. And the ground state of hafnia or zirconia is the 7-coordinated monoclinic phase, which is a high volume phase. But the more functional phase is this high temperature phase, which is a tetragonal phase. It's 8-fold coordinated, and this it's the commonly known fluorite phase, and this can either exist in a tetragonal phase or a cubic phase. And since this is a low volume phase, it can be stabilized by higher pressures, by applying pressure. Or dopants such as yttrium. Yttria stabilized zirconia is a good poster child example of one of these phases, or just by nanostructuring, where you are creating this huge amount of nanoparticle pressure to actually stabilize this low volume phases. But both these phases are quite nonpolar. So there is the polar orthorhombic phase that Uwe was talking about. Is a less symmetric phase than this tetragonal phase, and one of the common pathways of getting to this phase is to somehow try to reduce the symmetry of this, right, by applying inhomogeneous strain or Martensitic-like transformation. Okay, so but if we look at the entire spectrum of the polar phase of all the phases that exist in hafnia. So this is theoretically and experimentally predicted phases. The black shaded region is kind of a thumb rule of what you can get in thin film when you make thin films, and the blue shaded regions are actually all the predicted polar phases. So we see that the orthorhombic phase has the least energy. Whereas it's not impossible to attain other, let's say, phases, other polar phases in this material. So we started actually with the hypothesis as to whether we can stabilize a single phase polar hafnia, so as to study its ferroelectric properties without worrying about the non-polar surroundings and things like that. And as a result, we used pulse laser deposition to grow hafnia. So first we selected perovskite substrates. And LSMO is the back electrode. And we see that, okay, so this is, we have achieved epitaxial growth of a fluoride structure on a perovskite. And then you slap a top electrode on this, and then you measure the ferroelectric properties. We indeed see that a 9 nanometer thick film here in this case shows a smaller polarization of about 18 microcoulomb per centimeter square compared to a 5 nanometer film which shows double the polarization. So indeed, as you keep miniaturizing this hafnia-based thin films, or hafnia zirconia in this case, the polarization becomes more and more robust. So this is against the conventional ferroelectric materials, right? Since then, we started calling this new kind of ferroelectricity that exists in this hafnia-based materials. So these samples, which were epitaxially grown, were also wake-up free. The idea of wake-up was presented by Uwe before me. Okay, so this is the kind of ferroelectricity that we wanted to study. So we got it. So now let us try to look at the structural reasons as to why this ferroelectricity is stabilized. So indeed, here I present some X-ray diffraction theta to theta maps, and you see that as you keep reducing the thickness of these films, the this peak. This is the 111 out of plane peak. So these films are oriented along 111 out of plane. That shifts left, and that is a statement of out of plane elongation or in plane compression. And this strain, this in plane compressive strain, actually relaxes as you keep growing the films thicker and thicker. And in fact, it is the strain relaxation is pretty much concomitant with we not observing ferroelectricity at higher thicknesses. Okay, then we went further ahead and we did some texture analysis. So these are films which are grown along the 111 direction. And in any pseudo-cubic 111, there are four families of, there are four 111 planes in a family of 111. So if 111 is if the orientation is along 111, you should see three other 111s along this circle in this pole figure configuration. But what we see is 12 different 111s, and so that is a statement that we have four different domains which are rotated 90 degrees with respect to each other. We can do a symmetric theta 2 theta scan about one of these domains. Let's look at the blue domains, let's say. And then we see that these three 111s have a smaller lattice parameter than the 111 which goes out of plane. So there is a 3-to-1 multiplicity in terms of the 111 family of planes, the despacing of a 111 family of planes. And this 3-to-1 multiplicity is a characteristic of rhombohedral phase. It's not orthorhombic. So and our TEM analysis also supports this. So what we have indeed is a new rhombohedral polar phase on these perovskite substrates. Okay, so the domain structure looks something like this in the TEM. So here I'm showing you 180-degree domains. The important point that I want to make here is the size of the domains is quite commensurate with the thickness of the film. So if the film thickness is 10 nanometers, you have 10 nanometer sized domains. If the film thickness is 5 nanometers, you have 5 nanometer sized domains. That immediately gives us the idea that there is huge amount of pressures coming from this nanoscopic confinement here. We look back at the nanoparticle literature of hafnia and zirconia, which is quite well studied. And in this range of interest, we already see that in nanoparticles of hafnia, a cubic phase is already stabilized. So that gives us a simple model that you start with a cube growing along the 111 direction, and then the substrate applies an in-plane compressive strain, and that's how you're getting a rhombohedron. Okay, so this is the basic principle how we get the rhombohedral phase. So can we, like we do for other perovskite substrates, can we follow this laundry list of all the substrates and then see if we can stabilize or if we can find some trends in getting this rhombohedral phase? And indeed we did that. So as we move, okay, that's too much. So as we move along from perovskite substrates of a lower lattice parameter to a larger lattice parameter, we see first of all a textural evolution. So here the family of 111 planes correspond to a film that is oriented along 001 direction. Whereas as you move towards STO and scan dates, we see that this corresponds to a uniquely 111 oriented films. Whereas in between you have both 001 and 111 oriented grains. Okay, so and then we have seen earlier that in STO and also in dysprosium scan date, we have uniquely oriented but also a single rhombohedral phase when you think about films which are quite thin, less than 10 nanometers. So what happens in case of these mixed grain films? So we can look at this 111 orientation, and then we see that there's a 3-to-1 multiplicity. So these 111 oriented grains are rhombohedral. What about the 001 oriented grains? We can again do a similar kind of theta 2 theta scans, and then we see that there is a mixed phase. It's we can analyze what these phases are. These are the green and the red curves come from monoclinic phase, whereas the low volume phase indeed happens to be the tetragonal phase. So what we have is this 001 oriented films are a combination. I mean, they're nonpolar essentially. Okay, so that gives us another model where when you have a modest difference of lattice parameters between hafnia, zirconate and the substrate that you're using, the initial nucleation and process inside the PLD actually is tensile strain mediated. And then you get a cube-on-cube growth. Nevertheless, these are nonpolar phases. Whereas when the strain mismatch is quite large, What we have is a surface energy dominated growth, the initial nucleation process, and it is well known in hafnia based nanoparticles that 111 surfaces are quite least energy surfaces. Okay, and then once this starts growing along the 111 orientation, then you the conditions are such that the substrate would apply a small compressive strain, and that gives it the rhombohedral polarization. So, so far the lessons we learned from perovskite substrates seem to be that if you're trying to somehow get the 111 orientation, and in case of perovskites we are getting it through through surface energy considerations, we can, and then apply compressive strain, we can stabilize a rhombohedral phase. So can we test this by growing hafnia on other substrates? And the substrates we selected now were these hexagonal or trigonal substrates. So sapphire and gallium nitride. Both of them offer offer a template such that you are forcing hafnia to grow along the 111 direction, and then both of them offer a slight in-plane compressive strain to the growing hafnia. And indeed, you do see that there is a 3-to-1 multiplicity in both these substrates, and then we have a rhombohedral phase again. We did some more transmission electron microscopy for the hafnia zirconate grown on gallium nitride, and just by looking at this high angle angular dark field image, which is quite sensitive only to the cationic positions, we could already say that based on image simulations of this alternating elliptical like atomic columns, you could already say that this is an R phase. But that is just half the information, and the other half of information comes from this new technique called differential phase contrast imaging. This was more or less discovered in 2015, and this is quite similar to the first talk that we have, except that the probe sizes are quite small compared to the electric field mapping that was presented by Jason in the first talk. So essentially, we could image internal electric fields inside any material. So these are the atomic fields of the columns, and you integrate the atomic fields, you get the atomic potentials. You differentiate it, you get the atomic charge densities. And already from this raw image, you can see that there are oxygen columns in between these hafnia columns. Okay. So since we see oxygen, which is complete information, we could actually go ahead and then do further analysis. So first we can determine precisely by looking at the real space images, the space group. We can say that this is not an R3M. Our image simulations correspond more to an R3 kind of a phase group. And then we can also quantitatively analyze what kind of polarizations we are getting. So on gallium nitride, these are quite low. Nevertheless, this is along the 111 direction, corresponding to what rhombohedral phase should have polarizations. Well, so you can do more quantitative analysis using this kind of imaging. So a holy grail of all this is to be able to grow hafnia, this rhombohedral phase on silicon eventually. So far we have, okay, so you grow a hafnia along 111 direction and applies a compressive strain, you get a rhombohedral phase, right? So let us test that on silicon. And so for that, we again chose a 111 orientation of this silicon substrate. Sorry, 111 silicon substrate. But the epitaxy on silicon becomes quite tricky because of the presence of this native oxide layer on silicon. So we have to somehow scavenge off this native oxide layer, and that happens through this scavenging reaction in situ. Except that this reaction happens at high temperatures, so it's a backward reaction. So you will find some regions with a reformed amorphous silicon oxide, and you will find some regions with just the crystalline layer of zirconium oxide on which the epitaxy takes place. Okay, so indeed we get epitaxial, well-oriented films of hafnia on silicon oxide, and then we see that if there is an amorphous silicon oxide, this reformed silicon oxide, just on the top of that there is a monoclinic phase, a nonpolar phase. Whereas if there is a direct connection between the R phase and the silicon, we have, between hafnia and the silicon, we have the R phase. So indeed, so what is stabilizing this R phase? One is there is a 111 orientation, and what gives the R phase its compressive strain. Indeed, we find that in between silicon and hafnia, there is always this one monolayer of, yeah, I'm done. There is always this one monolayer of crystalline silicon oxide, cristobalite, which gives a very little compressive strain. And that reflects in terms of small rhombohedral distortions and also little polarization that you get. Okay, so all this while I've been telling you about the rhombohedral phase. So I would like to end by saying, do you ever see an orthorhombic phase? Yes, the one case where we see orthorhombic phase is when hafnia is grown on silicon 100 using similar techniques. But again, so here you see nice accordion patterns of this, but these come from monoclinic domains. But in between these accordion patterns, you have an orthorhombic phase of hafnia which is being stabilized. But this time it is growing along the 100 orientation. Okay, so with that, let me give you some take-home messages, which polar rhombohedral phase. So essentially, there's only one guideline, which is grow along 111 direction and apply a compressive strain. That gives you a rhombohedral phase, or so far, all the data seems to suggest so. And in case of perovskite substrates, this 111 orientation is imposed by surface energy constraints. And in case of hexagonal or silicon 111, it's the symmetry of the substrate that makes you grow along the 111 direction. With that, let me thank you for your attention and then thank all the funding agencies that have contributed to this work.
All right, any questions for our speaker?
I have a question regarding the film. You're saying that there's three phases?
Two phases. Oh, yeah, three phases.
Three phases, right?
Yes, yes.
Rhombohedral and a mixture of tetragonal and monoclinic?
Yes.
So you can basically, by changing the substrate, you can get a wide range of three-phase coexistence. Am I right?
Yes.
Is that against the Gibbs phase rule?
Why?
Is that against the rule of Gibbs phase rule? You have three phases coexistence. I assume your composition is homogeneous across the film. So you have no freedom. Suppose you should have zero freedom. Right? Yeah.
Zero freedom. At one particular temperature, you can only have.
The freedom equals C minus P plus 2, right? So
yes, yes. But again, we are assuming spatially. So from the TEM analysis, at least spatially, we see either just the tetragonal phase and the rhombohedral phase, or the monoclinic phase and the rhombohedral phase. So there is no one read. I don't know. So how do you interpret this this Gibbs phase rule? Yes, you're right.
It's not equilibrium.
Yeah, it's not equilibrium.
yeah, and this
Okay, fine.
Also can be inhomogeneous. Does zircon ever form on silicon when you have the the zircon doped or the hafnia zirconium phase? Does that form zircon in the interface with
the seed layer, is it zirconium oxide? Is that your question?
No, I'm asking about zircon, zirconium silicate.
Zirconium silicate. No, not in these conditions, but you can always form them when you're going at much lower pressures.
Oh, okay, but it's not forming.
Not in these conditions. We apply slightly larger pressures, yes.
All right, let's thank our speaker one more time.
I don't know what it is.
Are you talking about barium tightening or talking about hafnia?
Hafnia.
Did you find it?
It's coming. Okay, I think this is it.